Hello friends, this question is from the test series 11 from the subjects of analog, and the topic name is operational amplifier and its application. It's a linked data question. In the problem, we have one op-amp based network which is acting as a filter, because in the feedback path we have an inductor L and the capacitor C. Okay, and in the first problem, question says that in the circuit above, find the nature of the circuit, which type of filter the circuit is acting. So we have four options: low pass filter, high pass filter, band pass filter, and band reject filter. We need to find out which type of filter this system is. From which type of filter the system is acting. So now the best way to find this answer is, for any type of op-amp based active filter based question, is that you should always use the property of reactive elements towards its frequency. Like we know that Xc has a relation as 1 by 2 pi Fc, and XL has a relation as 2 pi FL. Okay, so now if I say, assume that my frequency is very low, let's say it is 0. So for very small range of frequencies, my Xc will tending towards infinity and XL is 0 in the same time. So if XL is infinity, so it will act as open circuit. So if my feedback path is acting as an open circuit, it means that my entire signal is either going to in the op-amp or from the RF, right? So this path is eventually acting as open circuit. So the filter has a virtually no role in the play of the operation. On the other hand, again I will put the very high value, let's say towards infinity or tending towards infinity. So if f is very high, then Xc is 0, but my XL is tending towards infinity because it is directly proportional to f. If f is very high, then XL is also very high. So again, because L and C are in series, so this time my C is 0 but my L is infinity. So because of L, we again have an open circuit network. Again my LC network is open circuit, so again it has no play on the circuit operation. My entire signal is going to pass with the system only. But if we can consider the third range, which is the cutoff frequency, for which this LC network is working in a resonance, for that cutoff frequency, which will be 1 upon 2 pi under root LC, depending upon the value of L and C, whatever that value is for that cutoff frequency, my XL is going to equal to XC. So this path is eventually act like a short circuit wire. So if this part is eventually act like a short circuit wire, then my RF will be shorted, then my entire input current is going to flow from the short circuit wire, and now there will be no current which is going to flow towards op-amp. So my op-amp is eventually not going to work for this frequency. So eventually this circuit is act like a band reject filter, because it passes the each and every frequency, but the only range of frequency at which my filter is in the resonance, for that range of frequencies this filter is moving out or leaving out. So this filter is behaving as a band reject filter. D part is the right answer. Okay, so that is D part is the right answer for the first part. Now for the second part, question directly says find out the transfer function of the V0 by Vin. So for the transfer function, our process is very simple. Just apply the nodal, name this node as a V and this node as a VP. Okay, from the virtual ground property, we know that Vn is equal to VP. Vn is equal to the VP, and I am going to apply the KCL at node Vn. So if I am going to apply the KCL at node Vn, so my expression will be Vin minus Vn by R. Okay, let's name this resistor as R, right? And you can observe that before applying the KCL here also, you can observe that in this circuit we have input and the inverting terminal. Okay, and the feedback path is RF parallel LNC. So my feedback resistor is basically RF dash, name it RF parallel XL plus XC. So my this entire network is acting like a inverting amplifier. So without applying KCL also, I can directly say that it is nothing but an inverting amplifier. So I can directly apply the formula of the inverting amplifier. So my V0 will be equal to the minus RF dash by R into Vs, which will be minus RF parallel XL plus XC by R times Vs, right? So now if I can find the V0 by Vs here, so it will be J times omega square, by simplifying this network obviously, J omega square LC minus 1 into RF upon omega RFC plus J times omega square LC minus 1. So this will be my expression. It's just a simple formula of the inverting amplifier, or the but you can solve it by the KCL also, but because we know that it's an inverting amplifier, so we can directly use the formulas of the inverting amplifier. So my correct option is option B here for this case. Option B is my correct option. Thank you.